This is a video lesson for 2.6, all the special functions. So the first example is creating a graph that shows cost of postage for different weights of letters. And if you can see, it says weight not over that amount of ounces. So for 1, the price would be 34 cents because 1 is not greater than 1. It's not over 1. So at 1, we know that the price is going to be 34 cents. At 2 is 55, 3 is 76, etc. What we need to figure out is weights in between those numbers. So the weight of your package was, or your letter, was 0.5 ounces, say. So its weight not over 1. So since 0.5 is not over 1, the price for that would be 34 cents. So I'm just going to put an X and Y here. So it'd be 34 cents. What about between 1 and 2? So like 1.2. Since that's not over 2, but it's over 1, so it has to be the 2-ounce price of 55 cents. And then between 2 and 3, like 2.3, it's not over 3, and it's greater than 2, so it's got to be the next price of 76 cents, etc. So we can see that for values between 0 and 1, not including 0, the price of the postage will be 34 cents, and that's that notation that you use. For between 1 and 2, not including 1 but including 2, the price is going to be 55 cents. And then between 2 and 3, not including 2 but including 3, the price will be 76 cents. And then 3 and 4, the price would be 97 cents. So we know that this graph is going to be a step graph because values in between there are all going to have the same output. So when we go to graph this, when you make your graph, we got to put a break in the graph first of all. And since we are going up, if you noticed, we are going up by 21 every time, 21 cents. So that's what I'm going to go up by on my y-axis. And the weight or the price is the y-axis because that depends on how much your letter weighs. So since the price is dependent, that goes on the y-axis. The independent variable is weight. That's the one that changes independently. So what we're going to want to do is put a break in the graph. So I whited out that section there, and I'm going to put my break. And so that shows that there's data that I didn't include because there's not data that I didn't include, but part of the graph I didn't include because there's no data there. And so what I want to start at is my starting point. So I'm going to start at 34 cents, and I'm going to go up by 21. So this would be 55, 76, and the last one is 97. So those are exactly the points that I want. So that's why I chose to go up by that much. And then for the x-axis, we're going to go up by 1s because that's our weight in ounces, and we got to make sure that we label it too. And be sure to put what measurement you're doing because it could be weight in pounds and price in cents or something like that. So we got to make sure we put what we're measuring in, weight in ounces, price in dollars. Okay, so there's your graph. Now all we have to do is plot those points. So I know that my price for 1 ounce is 34 cents. My price for 2 ounces is 55 cents. And my price for 3 is 76 and 4 is 97. And I knew by testing out some points what values in between cost as well. So a point we can add in here though is 0, 0, because we know that if you don't have a letter to mail, you don't have anything that you're not going to pay any money. So we're just going to put a point 0, 0 there. Now, any point after 0, any weight after 0 jumps up to 34 cents. So we have to put an open circle here and then a line. So that shows that any x value between 0 and 1 has an output of 34, but not including 0. And the reason we can't have that is because it wouldn't make sense that if you had a letter that weighed nothing or weren't mailing anything that you pay both $0 and 34 cents. So if they were both closed circles, that would not be a function, and it wouldn't make sense anyway. But anything in between 0 and 1 for our x value, for our weight, is all going to cost us 34 cents. And then at 1, is 34 cents. Any time after 1 jumps up to 55 cents. So we got an open circle and a line because anything in between 1 and 2 is also going to cost us 55 cents, including 2, not including 1. And you can see the pattern that's going on here, because then we jump up to 76 cents, I think. Yep, 76 cents. So any value in between 1 to 2 and 3, any weight between 2 and 3 ounces, including 3, not including 2, is going to be 76 cents. Get any greater than 3 jumps up to 97 cents, and that will keep going on in that fashion. Oops. So that is our step graph for that situation. So that's one of our special functions, is a step graph, and sometimes it can be written as a function, written like an equation written for them, and it's also called a greatest integer function. Is a function that represents a graph that consists of line segments or rays. So the one we just did was not a greatest integer function. It was more like a least integer function, but a greatest integer function looks like this. And so what those symbols means is you want to, just like if you had absolute value, you make that number positive, or figure out how far it is from 0, whatever's inside the absolute value bars. Well, this time for greatest integer function, you're going to take whatever's inside and change that number to be the greatest integer less than or equal to that number. So that can sound confusing, but it's really not too bad here. So if we had an example of 2.1. So I want to round, not really round, but because it's not the normal rounding rules. If it's above 0.5, you round up. We'll never round up in this case. It's always rounding down. So the greatest integer less than or equal to that number. So the two numbers that are around it are 2 and 3. 2.1 is between 2 and 3. Which one's lesser? And that's 2. So 2.1 is equal to 2, because you round it to the greatest integer, but that's less than that number. We can't choose 3 because it's not less than 2.1. So another example would be, it can be a little trickier when you have negative numbers. You just got to be careful. So if it was negative 2.9 in the greatest integer function, then negative 2.9 is between negative 2 and negative 3. Which one's smaller? Negative 3 is smaller than negative 2. It's a bigger number. The absolute value of that number is bigger, but 3 is more negative, so it's going to be less than negative 2. So we know that it has to be negative 3 because that's the number, the closest integer smaller than this number. Negative 2 would be bigger than that number, so it's not negative 2. So just be careful when you're plugging in negative numbers. So for any greatest integer function that you have to graph, all you need to do is make a table, make an XY table. And like I said, you always want to plug in points around the origin. There's no use in plugging in like negative 25. You don't want to do that big or extreme of a number. So we just want to plug points in around the origin so that we can just be, around here for the function. So we're going to graph the greatest integer function, the parent function, which is just the greatest integer function of x. So any number we plug in, we're just going to round it, not really round, but take the greatest integer less than that number. So whenever you have it, I suggest you do whole numbers first. So I'm going to do negative 3 to 3, but I'm going to leave a space in between right now, so I can do numbers in between. So I know that negative 3 will be negative 3, negative 2 is negative 2, because these are all integers, so their outputs are just going to be whatever that value is, because we're not doing anything afterwards. It's just that number x. But then I need to figure out where, what the outputs are for numbers in between them, because remember, we can only have integer outputs, so I got to figure out where, like a number between 2 and 3, negative 2 and negative 3, where what its output's going to be. Is it going to be negative 3 or negative 2? And remember, we know that it's supposed to look like a step function. I'm going to go ahead and just plot the whole number points that I already have. So I know that it's negative 3, negative 3, negative 2, negative 2, negative 1, as you can see, this is just like our parent function. So if we were to just draw a line through it, that's just our parent graph. But it's greatest integer function, so we can't have any of these heights in between the points. It's strictly integer heights because that's the output. We're taking the greatest integer, less than the 1 inside the brackets. So if I'm going to plug in a number here, like between -2 and -3, let's try -2.5. So the output is -2.5 in those special brackets. And so what number, integer, is the biggest one that's less than that number? So I know -2.5 is between -2 and -3, so it has to be -3 because it's got to be smaller than -2.5. Now I'll do like 1.3. And again, that's going to, I need the biggest integer that's smaller than that number, so that's going to equal -2. Between 0 and -1, I'm going to do -0.2. So a number, biggest integer that's less than that number would be -1, because 0 is bigger than -0.2. Between 0 and 1 is, I'm going to do 0.3. Again, it's between 0 and 1. The smaller of those two numbers is 0, so that has to have an output of 0. And then between 1 and 2, like 1.7, is going to go to 1, and 2.3 is going to go down to 2. Okay, so now I know where they go in between the integers. So this is what the XY table actually should look like. Any number between -3 and -2 we saw was going to have an output of -3, not including -2 though. So that's why over here I have not equal to with the 2, -2, and equal to with -3. So now all their outputs are going to be -3 for -2, and up to -1 but not including it is -2, then -1, 0, 1, 2, 3. So I can go ahead and plot those now. And remember, I know that that results in a bar and it looking like a step graph. So any inputs between -2 and -3 all have that output of -2. So it's got to jump up here. I'm in an output of -3, so it's down here actually. So then I know any of those outputs, -3, so close to open, because remember we can't have two outputs per input anyway. And I know at -1 or at -2, its output's actually -2, not -3. But every point until then is all -3. Same thing here, any value, x value between -1 and -2 all has an output of -2. Between 0 and -1, all the outputs are -1. And once you get a few, you can see the pattern and just go. I'm not doing the neatest job here, but that's okay. And then that is your parent function for the greatest integer function. And this is going to keep going up this way and down in that pattern. So anytime you're doing greatest integer function, just make an XY table, and that will help you figure out where the bars are going to go. So again, just remember that a dot means it's included, and an open circle means it's not included. Let's do another example here, and this one, you can't write a function for this one, but so it's going to be a little different, but it is a step graph because it says the psychologist charges for counseling sessions at a rate of 85 per hour or any fraction thereof. So if you spend even a minute over, like if your appointment's an hour and you spend just a little, like a minute over that hour, you got to pay for that full hour of his services. Or if you spend a half hour with him, you still have to pay for a full hour. So it's going to be a step graph. If it was just 85 an hour, then half an hour would be 42.50. If you only, because that's half of 85, but it's not a constant rate. And if it was a constant rate, then it would be a line. But this is going to be a step graph because you can only pay the psychologist increments of $85. So let's start out with 0. If you don't see the psychologist, you're not going to pay anything. If you go see him for 1 hour, then you have to pay $85. If you spend 2 hours there, then you have to pay $170. And if you spend $3 hours there, you have to spend $255. Then we know, because you have to pay for 85 any fraction of an hour, I know any x value between 0 and 1, I'm going to spend $85. So if I spend like half an hour there, so I'm going to put 0.5, I still got to pay $85. Then I know if I spend 1.5 hours, so an hour plus a little more, I still have to pay for the full 2 hours here. So I know I'm going to have to pay 170 still, and then between 2 and 3, if I just spend just a little over 2 hours, I still got to pay for 3 hours, so that's going to be $255, and go on in that fashion. For your graph, you got to know which one is the independent, which one's the dependent. The independent is the time, is the appointment time in hours, because that's the thing that changes. If your appointment's so long, this is how much you pay. You're not going to say, I'm going to pay this much. Tell me how long my appointment was. And then this is going to be price in dollars. Not is, in. And then for my scale down here, I'm just going to go by ones. And then for your Y scale, always go up by a convenient number. I know the increments are $85, and so I'm just going to go up by 85s. And luckily, it jumps, my starting value is the same thing as how much I want to go up by. That's why I don't have to put a break in my graph, because I know that this distance and this distance are the same. Now, if it was 85 an hour, but you had to pay 150 to start with, then I'd have to put a break and then go up by 85s. But this time it's nice, and we can just go up by 85s without having to put a break in the graph. Now we're just going to plot those points. So at 0, I know I'm not going to pay anything, because that doesn't make sense to even do that. 1, pay 85, 2, 173, 255, 4, and it will just keep going up like that. So I've got open to close this time, because as soon as you hit over 0 hours, you jump up to $85. And then you do that until 1 hour, and then any time after 1 hour, it's going to jump up here. You've got to do the open to close. So this is one of the reasons why you don't have a function for it, at least a greatest integer function for it, is because it's open to closed. And it will go on like before in that fashion. So now I can look at this graph and see how much I have to pay for an appointment. Okay, I spent 3 hours and 20 minutes, so that's between 3 and 4. So I pay $340. And that's it for the psychologist one. There are a couple more functions that are special: constant and identity. Identity we've seen before. That's just the parent graph for linear equations. It's the least complex form. The slope is just 1, and the y-intercept is just 0. So we start at the origin. So that's the least complex line that you can make. Constant function is a line, horizontal one, which means the slope is 0 and the equation is just y equals something. So this one's f of x equals 3. Remember, f of x is the same thing as y. So that is just a horizontal line, and that's called the constant function because it's just equaling a number. There's not two variables in it. And because there's not two variables, it doesn't matter what the x value is, the y value will always be 3, which is why it results in a horizontal line. A couple more of our special functions: absolute value and piecewise. So absolute value really is a piecewise function, but you don't need to treat it that way. You can just plug in points and find their output. So you make an xy table, plug in like -3 to 3, and then plot those points, and you're good. As long as you can see the shape of the graph, which for an absolute value function is a v. But what it's actually composed of is two equations, y equals -x and y equals x. So that's just a slope of 1 and -1. But I only want the line y equals x when x is negative. So if x is less than or equal to 0, I want the line -x. And when x is greater than 0, I want the line y equals +x. And so that's what that notation is saying. So basically, I'm graphing two pieces of a line, or one piece of two different lines. So for this line, I'm only graphing the piece where x values are less than 0. For this line, I'm only graphing the piece for when x is greater than or equal to 0. And then together, it's that one graph. So, but like I said, for absolute value, you can just plug in values and don't have to worry about the piecewise thing. But when you do have just a piecewise function that's not absolute value, you're going to have to do a little bit of thinking there. We are going to graph some absolute value functions, but first here's a review of the type of functions we've talked about so far. Step functions, constant, absolute value, and then piecewise. And that's what they look like. You should be able to, given a picture, distinguish between the different functions and be able to identify them. We can also talk about domain and range back on the psychology one. You can have any amount of hours to spend with the psychologist as long as it's greater than 0. So the domain, the x is greater than or equal to 0. And of course, there's going to be an ending point somewhere because he's only going to be willing to spend so much time with you. He's not going to spend 12 hours with you. So, but we don't know what that cutoff is. We're just going to leave it like that. And then the range is multiples of 85. You can't spend anything but a multiple of 85 since he charges you for a full hour for every, even a fraction of an hour. So that would be the range for the psychologist problem. I'm going to go a little out of order here and start with absolute value. I know on my flip chart I had piecewise first. But for absolute value, all we have to do is create an XY table and treat it like you would any other function you need to graph that you don't know the pattern for. Like for lines, you just graph the y-intercept, use the slope, you're good. But for any other function, you need to plug in points around the origin to start out with. So I'm going to plug in -3 to 3. So all I'm doing to the input is finding the absolute value of it. So the absolute value of -3, +3. Absolute value of -2, +2. +1, 0. Absolute value of 1 is 1. Absolute value of 2 is 2. And the absolute value of 3 is 3. Now I just need to plot those points. If you're unsure about where I'm getting those points, you need to see me. Or just go and actually plug in the points yourself. Instead of just taking my word for it, it might make a little more sense. All right, and so that's just my graph. And I can see that it's in the shape of the V, which I know it's supposed to be that way because it's absolute value. So I'm good. I'm done graphing that absolute value function. Now let's graph this one, which is a little bit different. We're still going to make the same XY table going from -3 to 3. But we just have to do a little more work. So I'll actually plug this one in. When you plug in x, you get -3 minus 4, the absolute value of that. Well, I know that -3 minus 4 is -7, and the absolute value of -7 is a +7. So my point is -3, -7. So I'll go ahead and graph that one, -3, -7. Or +7, not -7. That's this point right here. Then we have an input of -2, so it's going to be -2 minus 4 in absolute value bars. So it would be the absolute value -6, which is +6, so I can plot that point. -1 minus 4 is -5. Absolute value, that's +5. 0 minus 4, absolute value -4. It's +4. You see the pattern and get the point. 1 minus 3 would be -3. Absolute value is +3. Then 2 would be -2, but +2. 3 would be -1, but +1. So now I've got all these points. I can see it's just kind of going down, down 1 over 1. So let's go ahead and graph those. I go in just down 1 over 1 until an x value of 3. So I'm going to stop at 3 because I don't know where it goes after 3. It's not going to, and it won't go in that pattern. That it's not just going to keep going down because I know the equation is supposed to be a V shape. Well, I don't see a V shape right now, so I got to plug in some more points until I see that V shape. I know I'm not going to plug any points over here because I know that's going to keep going up. By coming down, that's not going to make a V shape. It's going to make an upside down V shape, which I know that's not what the graph is supposed to look like. So I got to keep going in the positive direction over here. So if you plug in 4 into the equation, and then 4 minus 4 is 0, so the output is 0. If you plug in 5 now, I'm going to move it over here. 5 minus 4 is 1, absolute value of 1 is 1. 6. 6 minus 4 is 2, absolute value of 2 is 2. Plug in 7. 7 minus 4 is 3, absolute value of 3 is 3. So I can see it's coming back up, and the next one's going to be 4, 5, 6. So now I can see the symmetry here and the pattern that it's coming back up. So now I can go back here and plot those points. So it's coming back up here. I know it's going to keep going on in that fashion. So I have a line going up, and I'm going to do that over here too, because it's going to keep going up in both directions. As far as domain and range for this one, you can plug any number in there because you can subtract 4 from any number, and then you can take the absolute value of any number. So domain is going to be all real numbers. All reals. I know it's really fat. And then the range is going to be, if you look on our graph, there is no value below 0. 0 is the smallest because this is going to keep on going up, and this piece is going to keep on going up. So there's no chance of any negative outputs. So your range is y is greater than or equal to 0. Or you could say all positive numbers and 0. Be sure not to say integers because it's not integers. There's any number in between as well. Because you plug in 3.2, be negative 0.8 and positive 0.8. So you can have any number for the output, just not negatives. So looking back at this one for domain and range as well, domain again is all real numbers because you can take the absolute value of any number. And then range again is the same thing as the other one. Y is greater than or equal to 0 because it doesn't drop below the x-axis, which would result in negative outputs. Now let's do a piecewise function. So we have a function that says you want to graph the function x minus 1 when x is less than or equal to 3, and you want to graph the function f of x equals negative 1 if x is greater than 3. So really, this is just a combination of two functions. So I'm just saying I want this function graphed and this function graphed. There are two different functions, but I only want the piece of this one where the x values are less than or equal to 3, and I only want the piece of this graph where the x values are greater than 3. So there are two ways you can do this. You can actually do xy tables, and for this xy table, start with 3 and go down. This one, start with 3 and go up. Or you can just graph both lines and erase the pieces that you don't need. I'm going to do the first one. I'm going to do some tables. So I know for the first function, I have to start with values 3 and less. So 3, 2, 1, 0, negative 1. And then you'll be able to see the pattern because you know, look, it's a line. The slope is negative 1, or is positive 1. So you can just use that to find more points. But to start out with, let's go ahead and just plug in some points. So if you plug in 3, 3 minus 1 is 2, 2, 2 minus 1 is 1, 1, 1 minus 1 is 0. And I can see it's just going down by 1. And the reason it's going down but the slope is positive is because my numbers are going down. Usually you start with lesser numbers, but I started with my biggest value there. So now I'm just going to plot these numbers. So I'm starting with 3, 2. Okay, so now we're going to plot our points starting with 3, 2. And remember, I'm going down, but really it's a positive slope because we read from left to right, so it's actually going up. But because I'm going backwards, I'm going down. So I keep going, and I know that line is going to go on forever in this direction. And really, it does go on forever in that direction, but I don't want that piece of the line. So that's actually not going to be part of my graph. I want it only to go until an x value of 3. Now I can make a table for my other one. Now notice this is just the line f of x equals negative 1. That's same thing as y equals negative 1. So there's nowhere to plug in an x. That means no matter what the x value is, my output is always negative 1, our horizontal line. So even though 3 is not included, I need to start with that number. So if 3 was going to be included, the output would be negative 1. 4, -1, 5, -1, 6, -1, everything -1. So what I just have to remember though is at 3, -1 has to be an open circle because I really don't want that point included. So I'm going to zoom in here and go to -1 for all x values after +3. So if it was on the line -3, I would put a point there, but since it's not, I'm putting an open circle, and then I know it's just a horizontal line, so it's just going to go in that direction forever, so I put my arrow on there. And that's our piecewise function. I only graphed x minus 1 from 3 and below, and I only graphed the line y equals -1 from 3 and above, but not including 3. And no, there's not a difference between the thickness of the line. You don't make one thicker than the other. It's just I didn't change my pen thickness, so don't worry about that. For this one, I want to write an equation for a piecewise function. So this time I'm giving you the graph, and I want you to tell me f of x equals, and then give me the two equations that are being represented and their restrictions. So when do you use one over the other? So I can see that this piece of the graph I'm going to use when x is less than -2, because it's got an open circle for an x value of -2, but then it has a line which indicates a bunch of closed circles, a bunch of dots, showing that those x inputs have outputs on that line. So to figure out the equation of this line, all I have to do is use the graph. So I can see the slope because I can see this point right here. And so I know that the change in y is 2, or the change in x is 2, and the change in y is 1. So this is a slope of 1/2. So I know the slope of that line. So I know my function is going to be y equals, but I already have this f of x over there, so I don't need to write that, equals 1/2 x. And now I just have to find the y-intercept, and I made it nice for you. Go up 1 over 2 again, and there's your y-intercept. If we actually kept going, your y-intercept is going to be 3. So the function equation for that one is 1/2 x plus 3. And again, we know that's for x values less than -2. So you write if x is less than -2. Then for your other piece, we can see that's for x values greater than 2, because at 2 it has an output. I'm sorry, -2. And I don't think I wrote that over there, did I? Yeah, I did. Okay, so greater than -2, because it starts at -2, it actually has an output, and then any x values greater than -2, it has outputs for. And to find the equation of this line is even easier, because I can see the y-intercept right here is 2, and then I can get my slope is just -1. So -1x plus 2. Or you can just say -x. You don't have to say -1x. Plus 2 if x is greater than or equal to -2. And that's it. That is the piecewise function represented in that graph. Going back real quick for domain and range, for this one, I'm saying that x value is less than or equal to 3, use this. X value is greater than 3, use this. So I'm hitting all the x values. So domain is going to be all real numbers. And then for the range, I can see that the highest point of my graph is right here. The lowest point I can't see because it's going to go down forever. So this is the highest point, and every point in between is covered. Now if you look right here, it looks like -1 isn't covered, but all of these points have outputs of -1, and there's also an output of -1 on that graph. So I know it's this point and below. So the highest point, highest x value is y value is 2. So y is less than or equal to 2 is your range. Domain and range for this one, again, we have a highest point here, and both of these are going on forever down. So for your range, y is less than or equal to +4. And for your domain, all of the values are included again, because less than -2, greater than or equal to -2, that covers all of the x values. So domain is all reals. Okay, let's graph another absolute value one, the absolute value of x minus 4. So be careful on this one because you're taking the absolute value before you subtract 4. So again, we're going to do negative 3 to 3 to try to get a good picture of the graph. We might have to add stuff if we don't see the v. So first thing you do is plug in x here. So you want the absolute value of negative 3 is positive 3, minus 4 is negative 1. Then absolute value of negative 2 is positive 2, minus 4 is negative 2. Absolute value of negative 1 is 1, minus 4 is negative 3. And then you see the pattern, but you got to know where it stops. So just be careful of that. When you plug in 0, absolute value 0 is 0, 0 minus 4 is negative 4. Now when it comes back to 1, it's going to change. It's not going to be 5. So it's going to be absolute value of 1 is 1, minus 4 is negative 3. And then negative 2, kind of got off here. Negative 3, negative 2, and then negative 1. So I've got all those points, and I'm just going to plot those on my graph. So again, negative 3, I got to remember now, start off with negative 1, okay? Negative 3 was negative 1. That's not negative 3. Negative 3, negative 1, negative 2, negative 2, negative 1, negative 3, 0, negative 4, and then it comes back up. So I can see that it's coming back up in that pattern, and I can see the v, so that is a good graph there. And now we can talk about domain and range. Again, there's no number you can't take the absolute value of, so your domain is going to be all real numbers. And then for your range, it's a little different this time, just because the other absolute value graphs we've done have always been y is greater than or equal to 0. But if you notice, this negative 4 on the outside made it possible to have negative outputs for this absolute value function. So all it did was shift the graph down 4 units. So that negative 4 on the outside shifted the graph down 4 units. So the lowest point is now negative 4. So y is greater than or equal to negative 4. It will never go below that point, because the smallest an absolute value piece can be is 0. And then I'm only taking away negative 4. I'm not changing this number. So the smallest value this whole function can ever be is negative 4. So that's your cutoff, and anything bigger we can have. So y is greater than or equal to negative 4. Here's another absolute value that has a little different twist on it. You're timesing negative 2 by the absolute value. So again, I'm going to do negative 3 to 3. The absolute value of negative 3 is positive 3 times negative 2 is negative 6. Plug in negative 2. Negative 2 absolute value is 2. 2 times negative 2 is negative 4. Plug in negative 1 is positive 1 times negative 2 is negative 2. 0 would be 0. 1 would be negative 2 again. Negative 4, negative 6 is going to follow that pattern. So it looks very similar to our parent function, except that all the outputs are negative and 0 except 0, and then they're all 2 spaces away instead of 1. So notice that 2 is like the slope of our absolute value graph. So let's go and plot these points. So negative 3, negative 6, negative 2, negative 4, negative 2, negative 2, or no, I'm sorry, negative 1, negative 2, 0, and then 1, negative 2, 2, negative 4, and 3, negative 6. So we can see that pattern, and you can see that it's upside down. It's an upside down V. So it's a little skinnier because that 2, it's doubling all the outputs, and then it's upside down. So the 2 doubled all the outputs, and the negative flipped the graph over the x-axis. So this is actually a reflection graph. So anytime you have that negative on the outside, it's going to flip the graph upside down. And that's it for that absolute value graph. We'll do a couple more greatest integer function graphs, and then I'll let you go. X, Y here, plug in some values. Be careful here because now it's negative inside. I'm still going to do negative 3 to 3, and we'll just figure out in what the output will be for non-integers. So if I put in negative 3, it's actually going to change to a positive 3, and 3 plus 3 is 6. Negative 2 would change to a positive 2, and then it would be 5. negative 1, positive 1, so 4, 0, 0, so it'll be 3. Then 1 is a negative 1, because we plugged in a positive 1 here, so it's actually negative 1. Plus 3 is 2. 2 is actually negative 2, plus 3 is 1. And 3, negative 3 plus 3 is 0. So those are my whole points right now. So it's starting at negative 3, 6 and going down. Negative 3, 6, and we're just going down. Now we got to figure out where the steps go in the graph. So I'm going to ask myself, if I plug in a number between negative 2 and negative 3, where's it going to go? So if I plug in, like, say, negative 2.5, then that would change to positive 2.5 inside of these bars, plus 3. Positive 2.5 would round to 2, or go down to 2, and 2 plus 3 is an output of 5. So in between negative 3 and negative 2, my outputs are going to be 5. Between negative 3 and negative 2, my outputs are 5. Now if I choose a value between negative 1 and negative 2, like negative 1.7, changes to positive 1.7, which rounds to a 1, plus 3 is 4. So values between negative 1 and negative 2 are actually 4. Between negative 1 and negative 2, here, all the outputs are 4. So if you notice, this is a little different. It's open to close this time instead of closed to open. So then any number between negative 0 and negative 1 will have an output of positive 3. And then between x values of positive 1 and 0, I'll have an output of 2, etc. So this one is just a little different than our past ones because of that negative x inside. And again, that's going to go on in that fashion in each direction. Okay, we've got one more greatest integer function to do. We're going to do greatest integer function of x minus 5. So again, negative 3 to 3. So negative 3 minus 5 is negative 8, so that would be negative 8. Negative 2 minus 5 is negative 7. Negative 6, 0 minus 5 is negative 5. 1 minus 5 is negative 4. 2 minus 5 is negative 3. And 3 minus 5 is negative 2. So I'm going to plot all those points. So I'm starting with negative 3, negative 8, and going up by 1 every time. So I'm starting at negative 3, negative 8, and going up by 1s until 3, because that's the only points I plotted here. And now I need to figure out where the points go in between. So if I plug in a number between negative 2 and negative 3, like negative 2.5, say, negative 2.5 minus 5 is negative 7.5, and so that's going to go down to negative 8. So numbers between negative 3 and negative 2 have an output of negative 8. So between negative 3 and negative 2, down here negative 8. So this is our back to our normal graph because it had a positive x in the inside. So it's just going to be our normal step graph from closed to open this time. And you can go back and test points in between to make sure, but that will be your graph and it'll go on forever here, here. And that's it for your greatest integer function graphs. And this was your homework for that section. Make sure you get it done and let me know if you need any help. So a quick review, the easiest thing to do is just plug in points from negative 3 to 3 to help you find some points on the graph. For greatest integer function, you need to figure out where points in between are going to go. So you need to plug in a point in between each integer input that you do. And for absolute value, just plot those. And if you can't see the shape of the graph, which is supposed to be a V for absolute value, you need to keep going in either positive or negative direction to get some more points so that you can see the V. And then for a step function, just make sure that you label your axes, know which one's independent and dependent, and figure out if it's going to be open to closed or closed to open. And that's it.